once again for technical problem at our end, and now we are starting the program, and today's program is on fault analysis basically, and I welcome for this program Mr. Kamin Dave, who is very competent faculty and very senior faculty in this field, and he has more than 20 years of experience in the area of relay design development, power system design, system studies, load flow, relay coordinations, unit protection settings, stability studies, harmonic analysis, etc. He is delivering a number of papers and presenting papers in international level as well as national level. He has also rich experience in testing, commissioning, and application of protection relays, SCADA's wide area monitoring system, diagnostic testing and electrical equipment like generator, transformers, CT, and operating philosophy of power plants also. He had worked as marketing and application engineering manager at SEL and had been having involved in the customer presentations, implementations, various features in the SEL products and business promotion of the company in the field of power system protection applications. He had also worked for Ashida and controls and was responsible for development of smart solutions for power system protection and control. He is graduated in electrical engineering, also received professional academic educations and certifications on power system study, advanced power system protection, and electrical equipment diagnostics for Indian Institute of Technology. He has received senior executive education and international business management from Indian Institute of Management. In a nutshell, I will say that he is a complete package of this program for fault analysis. His way of presentation is very nice. You will see yourself that you are taking so much interest during his session. Number of questions he is asking, I am telling you, and I request once again that be participative and give your answers and confirm your clarifications and what any problems you are getting facing at our your power stations that you should discuss with the Kamin Dave sir. And it is a great opportunity for us that we have done 2 days program with Patki Saab, and what Patki Saab has told in 2 days, that application will be definitely, he will application of that study will be today's, you will see in his program. And fault analysis, that is a very important subject, I can say heart of the your power stations. And I once again welcome Shri Kamin Dave Saab for today's program and request him to kindly start the program. Thank you, sir.
Thank you, Lambaji. Are you able to see the screen, sir?
Screen is not visible, sir.
screen is visible, sir, but your PPT is not visible. So you can just
Yes, yes,
minimize this screen. Yes, yes, yes.
yes,
PPT is
yes. Now
visible.
it's visible.
Okay, sir. So good morning, everybody. The outline of
Good morning, sir.
yes, sir. Good morning. Good morning. Very, very good morning, sir. Outline of today's discussion is a brief of the symmetrical components, power system faults, disturbance data analysis, case studies, and few points of the relay coordinations we will discuss today. Specifically for the overcurrent relay coordination feeder. Okay, so let us start with some basic is power generation, power transmission, and power distribution. Normally, the power generation as is done on 6.6 kV voltage level, 11 kV, 13.8 kV, 21 kV, 22 kV, 27 kV. Then it will step up to the bulk transmission in 220 kV, 66 kV, 220 kV, 400 kV, and then further step down to sub transmission 132 kV, 66 kV, 33 kV, to the distribution level to the 11 kV, 6.6 kV, 440 volt, 230 volt. This is the normally the power generation, transmission, distribution. Power generation specifically is done on the medium voltage like 6.6 kV, 11 kV. It depends on how much capacity of generator. It uh, it uh, the it depends on the how much current carrying capacity of the conductor ampacity. It depends on the how much voltage level of the generator, current capacity of generator, and size of the machines. For example, say if it is let us say instead of 6.6 kV or 11 kV, if we consider 66 kV, it requires very huge and bulky insulations. So the cost will be the machines will be very high. If we consider very low, like 3.3 kV for 80 megawatt machine or 100 megawatt machine, then the conductor size will be very high, large. And then in that case, again, the cost will be very high and I square R losses becomes very high. So optimal utilization of the generation, it is depends on the machine size of MVA and voltage level and then conductor size. Okay, so sequence component. Let us start with some basics. This is how the generator, what we can see here, the basics of stator winding, stator coils, rotor winding, rotor bars, and the rotor poles, two pole machines, four pole machines. Normally, if it is 3000 RPM, it is two pole machines, 1500 RPM, four pole machines. Specifically in a motor, it can go to six pole, eight pole, 10 poles. If it is heavy inertia of load like mines and coal mines and crusher motors and mill motors, something like that. So this is two pole machine typically 3000 RPM. So when we see here the north and south poles conditions, then north pole condition, it is on the right hand side. You look at it here, and this is a stator coil. So you look at here, the voltage is 0. When north pole is very close to the winding, it is maximum point 180 degree, sorry 90 degree. When it is north pole is, it is on opposite side of the uh, first point. I mean, it is 180 degree. You look at it here, it's rotated anti-clockwise. So it is 180 degree. And then it is when it is rotated further on 270 degree, it is opposite to the coil. It is 270 degree in a waveform. And then again it is 0 degree. So it is 0 degree. So that is the sinusoidal waveform. 0, 90, 180, 270 and 0 degree. Again it will be same condition, same thing will be get repeated. So this is how the sinusoidal waveform is generated for the single winding. This is how you look at it here. The window of this, so 0 to 360 degree, it is one window. That is called the one period of cycle. It is 20 milliseconds. So positive peak and negative peak. So when we look at it here, 0 degree, then anti-clockwise direction of phasors. This is 0, 45 degree, 90 degree, 135 degree, 180 degree, 225 degree, 270 degree, 315 degree, 0 degree. So that will be a one cycle. That will be a one cycle of phasor rotations. So if we can consider the three phase, then you look at it here, the rotor bars, the north pole is very close to the A phase coil, ABC phase. So A phase coil. So the waveform starts from 0, B phase, C phase. So that way you can look at it here, the A phase, B phase and C phase. A phase, B phase and C phase is mechanically apart, 120 degree apart. So that is 0 degree, 240 degree, 120 degree, the phasor rotations. A phase, B phase, C phase. You look at it here. This is how the three phase supply. Okay. So if we look at it here, this is A phase, B phase and C phase. So VAN is A phase to neutral voltage, VBN similarly, and VCN. So A phase to neutral, B phase to neutral, C phase to neutral voltage is 63 volt, 0 degree, 240 degree, 120 degree. Now if we can calculate, we do the phasor summation, we can get the VAB, VBA, VAB, VBC and VCA. So that is 109 at the rate 30 degree, 109 at the rate 270 degree, 109 at 150 degree. So this is how we can see here the phase to phase voltage. This is per phase voltage, VAB, BBC, VAB, BC, CA is a per phase to phase voltage. Okay, VAB. So VA angle minus VB angle. This is called VAB. VBC. VB angle minus VC angle. I'm not angle. VC magnitude at the right angle. I mean VAB, which means VA magnitude at the right angle minus VB magnitude at the right angle. VBC is VB magnitude at the right angle minus VC magnitude at the right angle. Similarly, VCA. So that is how we can calculate the VAB, VBC, VCA. Similarly, we can calculate the IAB, IBC, ICA. See, this is the important parameter when we look at it, the generator faults, generator protection, relays behavior, specifically line protection relays and line protection, line faults, what we analyze. That time, this type of the terms, parameters are more important to understand. How whether the VAB is properly calculated or not, IAB is properly calculated or not, what the ZAB we are getting, it is right or wrong, how the ZAB is calculating. That is how the we need to understand the some basics of power system faults. with these basic parameters. VAB is equal to VA minus VB. Similarly, IAB is equal to IA minus IB. Okay, so you look at it here. There is a one simple example which is demonstrated here. Is 63.5 volt enter at 5 degree, 63.5 volt enter at 245 degrees B phase, 63.5 volt enter at 125 degrees C phase. That is called pre-fault condition. And another condition is abnormal condition. You look at it, it's 63.5 volt enter at 30 degree, 63.5 at 270 degree, 63.5 at 150 degree. That is the second condition. So if you look at it here, this is per phase voltage. In a left side, if you can screen, you see the phasors, that is per phase voltage. Right side, this is phase to phase voltage. So when we extract the fault data, we need to understand that what is the quantity of. Many times I have seen in a fault the VA, VB, VC, like VA is not much fall down, but VAB is fall down. That is why the relay is got operated. So that is how we have to understand the exact parameters. How we need to understand first of all the power system calculation, and second we need to understand the relay algorithm, and then we can try to correlate both the things and then try to understand whether it is right or wrong operation on the particular fault. Okay, so this is how you look at it here. This is a three-phase generator. So winding 1, winding 2, winding 3, A phase, B phase, C phase. So that is coils are wound on the stator bars, stator cores, and this is rotor bars. So you can look at it, the rotor windings, and then you look at it here. This is A phase, B phase, and C phase terminals, and the other end of the coil is just got shorted and then it is grounded. It may be in a small machine, it will be a solidly grounded. It will be a intermediate machine, something like 20 megawatt, 30 megawatt machines. It will be NGR grounding, and then 100 megawatt machines, 250 megawatt machines, it will be NGT through NGR grounding. So grounding is depends on the networks, fault calculation, and those kind of other parameters. But yes, this is how we can do the grounding with the second coil, second end of the coils. You look at it here. Okay, sinusoidal functions. What is a phasor? Phasor is normally the characterized and associated with the magnitude and phase angle. So look at it here. For example, say A phase voltage 63 volt at the rate minus 10 degree. That is called phasor. 63 is a magnitude, minus 10 is the phase. So the phasor is 63 at the rate minus 10 degree. So 63 at the rate minus 10 degree is called the phasor of A phase voltage. Similarly, B phase, C phase, and then similarly it is for the current also. So Y at time is equal to Ym cos omega t plus omega t plus phi or theta. Sometimes people are calculate with sin omega t plus theta. Some people calculate the cos omega t plus theta. That depends on the phasor reference and where we put the zero crossings. That is the main important into the devices, numerical devices. If the zero crossing starts from the 0, that the reference is Ym sin omega t plus theta. If the zero crossing starts from the 90 degree, then Ym cos omega t plus theta. Normally in a relay, we consider Ym sine omega t plus theta as zero crossing, it is on the zero. Normally in a PMU, we consider Ym cos omega t plus theta. That is, we can also consider the sine omega t plus theta, but only the advantage is the PMU works on the real time clock and timestamp. So that will be the advantage, so that it can calculate on Ym cos omega t plus theta. But that is called the phasor calculation. PMA, which means phasor measurement unit. I think you must be acquainted with phasor measurement unit. Okay, so this is how the phasors is scalar quantity of phasor y is equal to real component of y plus imaginary component of y is equal to y at the rate angle. Y at the rate angle. Other way of the we can calculate it, the scalar quantity of y is equal to the under root real quantity of y square plus imaginary quantity of y squares. And theta or phi is equal to tan inverse imaginary component divided by the real component. Normally we used such type of terms for the line protection, as well as is for the generator protection. Z1 is equal to, for example, say phi plus j 10. Let us example say. So we can calculate z angle or line angle is equal to tan inverse x by r. Similarly, for the generator terms also we can calculate the tan inverse x by r. I mean, what are the impedance angle of the generators, that we can calculate through this thing. So that is how the terms is explained here. You look at it here. So that is how the y scalar quantity is y cos theta or cos phi plus y sin theta or sin phi. I mean, you look at it here. So cos y,
Excuse me, sir.
yes, yes,
Uh,
yes.
Please hide the sharing pop-up.
Okay, right.
Thank you, sir.
Okay, thanks. Okay, so you look at it here, the y real component is equal to y cos phi, imaginary component is equal to y sin phi. So every phasor is associated with a real component and imaginary component. So we, for example, say VA. So VA is equal to VA. If you can calculate VA, so VA is equal to VA cos phi plus VA sin phi. That is how I can calculate the VA. The other way of around is to VA is square root of the real component of VA square plus imaginary component of VA square. That is how we can calculate the VA. And then the VA angle is equal to tan inverse y sin phi divided by y cos phi. So that is the VA angle. Normally the relay calculates any numerical devices in power system. You can have a example of relay, you can have example of meter, you can have example of power quality meter, you can have example of renewable meters. I mean, revenue meters, you can have an example of PMU, any that these are calculating in a calculate the phasors in such a way that. So look at it here, VA is equal to 63 volt at the rate 10 degree. So rectangular form is VA cos 10 plus VA sin 10. That is called the rectangular form. And polar form, if we can say what, see there are in power system we can represent the things in a two ways, either in a polar form or rectangular form. The polar form, which means VA is equal to 63 volt at the rate 10 degrees. Rectangular form, which means VA is equal to VA cos 10 plus VA sin 10. That is how the rectangular form. Similarly, in a current, IA enter at minus 20 degree. So IA is equal to IA cos minus 20 plus IA sine minus 20 degree. So that is how we can see the polar form versus rectangular form. Somewhere we see why it is important that to understand when we are going to test the relay by using a numerical test kit like double omicron test kit, any you take it any. So in that during that time they shows the polar form, rectangular form. So we sometimes I see the mistakes that people are interpretation itself is wrong during a testing of the injection of fault. What they are injecting actually, it is the values are written in a polar form or rectangular form, and then they do the wrong injection and then they see the relay simulations. So that is how the practical things I have seen. So specifically we need to understand what the data is shown in a software is polar form or rectangular form. If it is rectangular form, then you can see in a polar form, convert into polar form or see in a polar form, and then you can inject. That will be a much easier. That 63 volt at the red 10 degree you are injecting, something like that. Okay, so slow phasor rotations. Phasor rotations. Sometimes we see the in a most of the times when we do the synchronization, the wording is the phasor rotation is most common. Let us say it's phasor rotation is fast or slow. Then when we do the testing of relay, then we see the specifically the under frequency relays testing or over frequency relay testing or DF by T relay testing. We have a terms of the frequency is 49.5 hertz or maybe a 50.5 hertz, something like that. So what does this mean of this? It is phasor rotations. Frequency is associated with the phasor rotations. So let us say slow phasor rotations. What is a slow phasor rotation? Slow phasor rotations, let us say if the power system frequency is 49 cycles per second, then the period is 1 uh, divided by frequency is equal to 0.0204, so 20.4 milliseconds. So 20, the window of 20 cycle window is now got increased to 20.4. So that is how the window of power system cycle is got increased. So if you look at it for the another 4 cycle, so first cycle window, and compare with the 20 milliseconds window. So blue color is shows the 20 window of 20 milliseconds, and the brown color shows is 49 hertz, which means 20.4 millisecond window. So you see the error is reproduced. So sometimes if there is a fault and there is a fault frequency is slightly changed. Let us say the 49.9 frequency 49.9 hertz 95 hertz during a load condition, and that is got changed to 49.7 during a fault condition. So in that case, we need to understand somewhere whether the equipment is capable to measure the such type of the phasor rotation or not. I mean, frequency tracking is there or not to track the correct frequency, whether the frequency is 49.7. So the phasors plotting I mean that values, data values are has to be tracked based on the 50 hertz component rather than the 49.7. It has the window has to be aligned again with the 50 hertz component. Otherwise, the fault quantity will be understanding of an analysis will be wrong in that case. If you so this is how you look at it here, the 1 cycle window for 50 hertz and 1 cycle window of 49 hertz. If it is four cycle 2 cycle window, let us say in a 2 cycle window, or 3 cycle window. When the window is increases, the error will be increases. So error increase, decrease, increase, decrease. This is a phasor rotation. That is how we see in even the synchroscope also during a synchronization. If the frequencies are when we try to match the frequencies 49 hertz, 49.5 hertz, and then we if the grid frequency is 49.97 hertz, and when we try to match the with the 49.97, 49.99, then the phasor rotation is very accurate, close to the 49.97 hertz of grid frequency, and it will be get a very slow in that case. Accurate in that case. Here you see the when the difference is increases, the I mean the when the period is sometimes when you do the 49 hertz, what will happen in a synchronoscope? Some it will go faster and then it will go slower, faster, slower, faster, slower, something like that, because the windowing will be matched in the such a way that over a period, 1 second window, another 1 second window, another 1 second window, something like that. Normally, we represent the frequency is 50 cycles per second. So it is 49 cycle per second, let us say. So in a one window, you will see the faster rotations, slower rotations, faster rotations, slower rotations. If the frequency difference is sleep frequency difference is 1 hertz. So this is how the frequency difference, you look at it here for the 3 cycle window, you look at it. Similarly, if you say the fast phasor rotations, so if it is 51 hertz, then 51 hertz, which means you look at it here, it is 19.6 millisecond window. If 50 hertz, it is 20 millisecond window. The window is now become reduced in that case. So it is a faster rotation. So normally, see why? Because when there is a over frequency into the system, the devices has to be measured the correct frequency according to the windowing system. So that frequency tracking has to be worked properly. So this is how you see the fast phasor rotations, 50 hertz. So phasor has to be readjusted according to the 50 hertz component. That is called the frequency tracking. Otherwise, we will get the wrong frequency values in that case. The representation of phasor and impedance. We have discussed about the phasors. What is a phasor? So VA at the rate 63 volt at the rate minus 10 degree or plus 10 degree, that is called the VA phasors. IA is equal to 1 ampere at the rate minus 20 degree, let us say, that is called the IA phasors. Now the combination of these two phasors, let us say V by I. So V at the rate angle of V divided by I at the rate angle of I. So V by I angle, voltage angle minus current angle is equal to Z phi. So that is the combination of two phasors. Is the third phasor we get is which is called the Z phasors. Z. So Z at the rate angle. So again, it is a same thing like polar quantity Z at the rate angle. For example, say 63 volt and 63 volt at the rate 0 degree, I is equal to 1 ampere at the rate 0 degree. So 63 ohms at the rate 0 degree. So 63 ohms is equal to real component plus imaginary component is equal to Z cos 0 degree plus Z sine 0 degree. So again, it will be comes into the convert into the rectangular quantity. I mean polar quantity to rectangular quantity. Z is equal to Z real part of Z plus imaginary part of Z. So this can be converted into either of the way to understanding of this thing. That see, this is how we can verify the whether the what the data we received that is right or wrong. अगर हमें जो डेटा मिल रहा है वो डेटा मान लो कि आप कोई पावर सिस्टम में कोई फॉल्ट हुआ है, समझो वो फॉल्ट का डेटा ही सही नहीं है, तो हम क्या एनालिसिस करेंगे उसके ऊपर? पहले वो तो कंफर्म होना चाहिए कि वो डेटा सही है कि गलत है. So that is how the such type of the techniques are more useful to understand, to compile the data and to understand whether this is right or wrong. So, कई बार ऐसा भी होता है कि हमें वो डेटा सही नहीं मिलता है, तो हमें अलग तरीके से उसको या तो वो इस रिले टेस्टिंग्स में सही आ रहा है फॉल्ट के ऊपर. फॉल्ट अगर मैं फॉल्ट प्ले कर रहा हूँ तो सही नहीं आ रहा है, बट मैं ओमिक्रॉन से टेस्ट इंजेक्ट कर रहा हूँ तो सही आ रहा है. So we try to analyze those things in a proper way, fault recording data, whether the fault recording is okay or not. This is so we can try to apply the multiple of the things in this way, that whether my Z is okay or not. See, most of the time when we do the testing of typical protection functions, like loss of excitation, like pole slipping functions, DFIDT functions, then line relay testings, then it is more important to understand the how to analyze the data. So with voltage, simple voltage functions and current functions, yes, it can be easily test with any of the test kits. So fault analysis is more important, how to interpret the data, whether the data is right or wrong, or how to convert into the other way of see to how to match the data with expected values. So that is how it has to be analyzed properly. So if you look at it here, let us see here, we have seen that Z at a scalar quantity. I mean, in a polar form Z at the right angle, in rectangular form Z at the right real plus imaginary component. So if I can say Z is the radius, small r is the radius, so that radius is the Z value in Rx plane diagram. So Z equal to R plus Jx, so resistance plus reactance, or reactance plus capacitance. So Z is equal to square root of R square plus XL minus XC squares, or apparent X squares. This is how we can see the Z area. Z area is less or equal to the radius of Z. This is how we can look at it here. Normally the backup impedance function and source kind of the function to try to understand with more with such type of the things, whether the backup fault is there and then how the relay is detecting those kind of things. Some manufacturers follows the non-directional impedance function, like MICOM relays and those. Some MICOM is, and some manufacturers they use the non-directional impedance, but it's a polygon characteristics, not a circle characteristics. MICOM use the circle characteristics like this. Whether the Ciprotec use the polygon characteristics, and the ABB gives the unidirectional characteristics of circle, which is called Moe characteristics or offset Moe characteristics. So that has to be understood properly whether how the Z function works. Okay, so the representation of phasor and impedance. Normally we have seen in the, there are there are power system faults, many types of the power system faults. Phase to phase, phase to ground, three-phase faults, double line to ground faults. But that fault has to be analyzed in a some analysis has to be done in a multiple way, and then detection has to be done by the relays, and then the relay has to calculate some algorithms. That algorithm is based on the impedance, basic calculation of power system impedances, if it is impedance based relays. So there are basic 6 impedances, which ZI is equal to VA magnitude at the rate angle divided by IA magnitude at the rate angle. So ZA magnitude, ZB magnitude, sorry, ZA angle, ZA impedance, ZB impedance, ZC impedance. Similarly, ZAB impedance, ZBC impedance, ZCA impedance. See, there was I have one example of one of the power plant which is having a 660 megawatt machines. There was a line fault, and backup protection relay is got operated. Actually, according to their settings, it should not operate, but it was operated. Whereas the other places there was 500 megawatt machine, and there was a GT terminal fault. GT terminal. Then also backup impedance is not operated. So relay setting is there. Manufacturers has done the given a set settings, but that settings are right or wrong. Who can validate? According to the fault, the setting has to be implemented. So relay calculates the, for example, say backup impedance relay calculates the normally phase to phase fault or three phase fault, not phase to ground fault. Phase to ground fault loop is off, as normally in the thermal power station. The reason is the generator is grounded and there is a GT is a delta star. So they normally keep the for backup coverage. It's only the phase to phase and phase to or three phase fault is required to be detected, not phase to ground. Again, the phase to ground is current is very less, like 14 ampere, 10 ampere, because it is restricted by NGT through NGR. So anyhow, it will be not detected by this relay. So only the phase to phase loop or phase two or three phase loop has to be detected. But 30-degree compensation is required, because there is a delta star transformer YD11 transformer. So YD11 is 30-degree differences has to be compensated. If there is a HV side fault, EHV side fault, because relays location it is on the medium voltage side, 11 kV side, 21 kV side on generator terminal, and relay has to see the fault on 220 kV side also, and relay has to see the fault on the 11 kV side also or 21 kV side also, from bus duct to the primary winding of the generator, generator transformer, and then secondary winding to EHV winding to the EHV switchyard fault, as well as some of a certain extent up to line faults. 10% of line, 20% of line, according to the impedance calculations. So relay is set to cover the switchyard fault, but the relay is not operated. So manufacturer has given a ZAB is equal to VAB divided by IAB. That is fine. Then what has to be 30? What has to do with 30-degree compensation? The second manufacturer has given a ZAB divided by IA. What has to do with this thing? That so one is a power system fault. The second one is the relay algorithm. that has to be understood and evaluated according to the power system faults, and then the setting has to be done into the relay. Then I explained to this thing that your setting has to be like this way, then only it will cover your fault. I see there are two things: either the fault has to be covered from EHV side, from Y to the EHV side, or else you can cover the busted fault, because the algorithm has to be work in this way, or else you can use the zone 1 is for this and zone 2 is for this in a backup impedance. So that way you can understand first of all the fault phenomena, and then the relay algorithm, and fault according to the fault phenomena we calculate the real impedance which is recorded by the relay, recorded by the through the waveform, and then we try to understand the relay algorithm, and then we need to fit into the relay the settings. Okay, symmetrical components. Yes, this is a method. It is discovered in 1913 by Charles L. Further, it was uh, done by another person, which is in 1920, and it was established in 1923 or 24. It was a one method that scientist was try to has developed a polyphase motor, and then he was try to doing a further research on the motor induction motor. The induction motor was somehow this got heated and burnt it. So he was trying to finding investigating the behavior of induction motor, why the induction motor is got burnt, and then he tried to uh, analyze the some of the power system conditions like three phase balance condition. Then if you can remove the one phase, then what will happen? If you remove the two phases and apply to the motor, then what will happen? So that way he derived a one method which is called a one, that method is called the symmetrical component method, and later it was established as the to understand the power system phenomena of in an electric network. So that is how the story of symmetrical component. That component is at, applied to utilize method to understand the power system relaying operation. So because the numerical relays works on all the numerical relays are the phasor based relays. Phasor. We discussed about phasor. So all the relays are phasor based relays, and they do the calculations like what we had discussed in above slides. The VA, I mean voltage, current, impedance, and then it converts into the rectangular form, and then converted into the further sequence component, and then it try to take the decision that whether the relay I need to operate or not, something like that. So method to understand the power system relaying operation, whether the relays are operating correctly or not, because the relays algorithms are based on these only. Relay measurement starts with symmetrical components. Yes, relay as we discussed, it is phasor based relays, and phasor based relays calculate the symmetrical components, and then it starts all the logic, maximum logic, critical logics that involves with the sequence component interlocks. So measurement itself starts with the symmetrical component during a fault condition. Method to analyze the power system scenario, whether power systems you if you look at it, the power system scenario, whether the balance condition, unbalanced condition, then how we can decide the fault condition, that is all the things scenario. Power swing condition, then what is happening, then pole slipping condition, then what is happening, what it is happening. most of the conditions, if conductor is breaks, then what it is happening. So these symmetrical components are trying to analyze the power system scenario. And method to understand the power system quality of network. Yes. See, when the harmonics are involved, power system quality is depends on the total harmonic distortion of waveform. Okay. So that how the total harmonic distortion, that is the when harmonic introduced into the fundamental components, it distort the sine waves, and when it distort it, the negative sequence or zero sequence components will be get introduced. So that we try to analyze through this thing, that we will see in the next slides how to analyze this thing that. So power quality meters calculate the power quality through symmetrical components. That has to be a harmonics and symmetrical component, combination of these two things. Method to analyze the postmortem of power system and electrical equipment faults. So when there is a fault into the network or equipment fault, like transformer fault, transformer even many of the most of the functions, it works based on the that logic works on the interlocks of the symmetrical components. So we try to understand of this thing that during an analysis of post-mortem analysis of power system faults. Okay, so balanced system versus unbalanced system. Balanced system, which means IA, IB, IC. You can see the left side, IA, IB, IC. All three are the balanced in a magnitude, equal magnitude, and equally apart, 120-degree apart. So that is called balanced system. Normally, the normal power system consider is a balanced system. The unbalanced system, the IA magnitude of IA, IB, IC are not equal. Even that phase is not even equally apart. So unbalanced system. Normally fault condition, motor start condition, transformer charging condition, capacitor charging condition, cable charging, when it is a long cable and we can close the breaker, we can see the waveform. That is not a symmetrical waveform. So those conditions, those are the phenomenon is unbalanced systems. Motor running condition and unbalanced, that is also unbalanced. I mean load jamming, something like that. So in balanced system, how you look at it here, IA 0 degree, IB 240 degree or minus 120 degree, IC 120 degree. So define alpha factor. Alpha is equal to 1 enter at 120 degree. So IA is equal to I, IB is equal to alpha square I, and IC is equal to alpha I. That is a positive sequence component. That is positive sequence component, and that is normally when the system is got balanced, the positive sequence component will be a 99.9% or 99%, something like that. It will most significant component is positive sequence component when the system is got balanced. So look at it here, the IA, IB and IC, the phasor rotation is 0, 240 and 120 degree. That is called positive sequence component. The negative sequence component is IA, IC and IB, 0, 120 and 240 degree is with respect to load, actually, generation and load. If generator is 0, 240, 120 and load 0, 240, 120, that is positive sequence. If generator is 0, 240, 120, if load is 0, 120, 240, it's negative sequence. If load 0, 240, 120, but generator 0 will reverse, that is 0, 120, 240 is called negative sequence. So negative sequence is opposite to the positive sequence. So I2 is equal to minus I1. Zero sequence. Zero sequence, which means there is no sequence, is called zero sequence. There is nothing is any sequences. All are in the same directions. So I1 is equal to I2 is equal to I0 is called zero sequence. So if we look at it here, in a balanced network, unbalanced network, or it is a fault condition, let us say it is A phase to ground fault. So IA, IB, IC, you look at it here, the phasor, how it is phasor. IA current is very high. So IA is equal to the positive sequence current plus negative sequence current plus zero sequence current. So any phasor, you take any phasor like balanced phasor or unbalanced phasor. Balanced phasor is also having a positive sequence plus negative sequence plus zero sequence. But in balanced phasor, the positive sequence is 98%, then negative sequence is 1%, 1.8%, zero sequence is 0.2%, something like that. If it is unbalanced phase to ground fault, let us say, then we will see the positive sequence plus negative sequence plus zero sequence. So positive sequence is, for example, say 50%. The negative sequence is, for example, say 30%. Or negative, some, if it is 100% phase reversal, let us say, like in a motor, sometimes during a commissioning or cable termination, the mistake has been done many places. So that is called 100% phase reversal. So the negative sequence current is 100%, almost 98% current is negative sequence current in that case. So unbalanced phasor is any phasor is equal to positive sequence plus negative sequence plus zero sequence component. And this, based on this component, we can identify whether the condition is this condition or this condition. Balanced condition, unbalanced condition. Unbalanced condition, then there is a three-phase fault, phase-to-phase fault, phase-to-ground fault, or unbalanced loading condition, power swing condition, pole slipping condition, right? Balance condition, what are the harmonics? If an harmonic of conditions and analysis based on this components. Okay, so if you look at it here, so this is a positive sequence component. So positive sequence component, balanced power system condition, you see the A phase, B phase and C phase current. So A phase current 0 degree, B phase yes 240 degree, C phase 120 degree. That you look at it here. Now if you look at it on phasor symmetrical component, 63 volt enter at 0 degree, 63 volt enter at 240 degree, 63 volt enter at 120 degree. So V1, V2, V0. So red color is V1. So now you look at it, V1 is 63 watt almost. And V2 and V0 is completely zero. So V1 plus V2 plus V0 is equal to V1 only, because V2 and V0 is equal to 0 in that case. So V1 is equal to 63 watt. You look at it here, right? So that is called the power system is got balance conditions. When is phase reversal? Let us say 63 volt enter at 0 degree, 63 volt enter at 120 degree, 63 volt enter at 240 degree. It's 100% phase reversal. that negative sequence component is become very high, is 63 watt. So V1 plus V2 plus V0 is equal to 63, but V1 plus V2 plus V0 is equal to V2 only, because V1 and V0 is equal to 0. So V2 is 63, 63 watt. Negative sequence component is very high in this case. So we understand if it is 100% phase reversal, which means the motors severe heatings will be start into the induction motors during a start conditions. Normally start condition and run condition, any condition. If it is 100% phase reversal, which means it is a lock rotor conditions, and the severe heatings will be starts into the motors. So look at it here. So for example, say 5% of voltage unbalance during a starting of induction motor generate a 30% of negative sequence current in network. But for example, log rotor current is 6 into 6 times of full load currents. So 5% of voltage unbalance. So I2 is equal to 6 into 0.05 is equal to 0.3 pu. So 5% unbalance in a voltage generate a 30% unbalance in a, or 30% negative sequence current in network. That is why normally we keep the negative sequence settings. This first stage is 20% with time is, for example, say 30 seconds. The second stage is, for example, say 50% or 60% with time delay is 1 second or 0.5 seconds, because it has to allow during a motor start conditions. So that is how we can do the settings of relay. 5% of unbalanced voltage creates 30% of negative sequence current in a network during a motor start conditions. Okay. Similarly, when we talk about the sequence component, is positive sequence voltage, negative sequence voltage, zero sequence voltage, positive sequence current, negative sequence current, and zero sequence current. Similarly, we can also see the sequence impedances. Z1 is equal to V1 magnitude enter at angle divided by I1 magnitude enter at angle. So that is called positive sequence impedance. Similarly, the negative sequence impedance and zero sequence impedances. Normally, when we look at it, the line parameters, line relay, when we do the line relay settings, we always ask the impedance parameters. Let us say 0.5 plus 1.5 ohms, so R plus JX. That is called the positive sequence parameter of the line. Z1 setting. That is Z1 parameter. And we also calculate the residual compensation factor of for to cover the tower footing resistance and arc resistance fault in a line, transmission line. For that, we can see the Z0 minus Z1 divided by 3Z1. That is the residual compensation factors. These factors will be calculated in a other way also, but more, in any way, the zero sequence and positive sequence impedance are getting involved. Some manufacturers calculate Z0 by Z1 in relay. Some manufacturers calculate Z0 minus Z1 divided by 3Z1. Some manufacturers calculate R0 minus R1 divided by 3R1 plus X0 minus X1 divided by 3X1. That is a R plus JX form. That is rectangular form of Z0. Residual compensation factors. So that is how we can use it is Z1, Z2, Z0. This thing that. So Z1 positive sequence impedance, Z2 is negative sequence impedance, Z0 is a zero sequence impedance. Okay, when we talk about the harmonics, then we can think of fundamental component. What is fundamental component? So because normally we used to talk fundamental component. Fundamental component is 0, 240, 120 degree. So R phase 0, A phase 0, B phase 240, C phase 120 degree is positive sequence component. As we have seen in the earlier slide, the positive sequence component is almost 98 to 99% in a balanced vector or phasor. So 0, 240, 120 degree is a positive sequence component. When we set second harmonic, then 0 into 2 is equal to 0, 240 into 2 is 480, 120 into 2 is a 240. So 0 into 2 is a 0, 240 into 2 is a 480, which means 480 minus 360 is 120 degree, and 120 into 2 is a 240. So 0, 120 degree, 240 degree. So that is A phase is 0 degree, B phase is 120 degree, C phase is 240 degree, is called negative sequence. When there is a second harmonic, the negative sequence component will be significantly increased. Third harmonic. So normal when we talk about the during a transformer charging, we can say the second harmonic component is present to, for example, say 40 to 45%. Okay, 40 to 50%. You see there is a negative sequence component will be high, and you see that transformer inrush current is not a balanced vector; it is an unbalanced vector. It is a normally a unipolar waveform or distorted waveform. That is why we can say it is an inrush current. It's not a regular current, normal current. Third harmonic is 0 into 3 is equal to 0 degree. 240 into 3 is 720 degree. 120 into 3 is a 360 degrees. So 0 degree, A phase on 0 degree, B phase on 720 degree. 720 degree, which means 360 into 360. So that, sorry, 360 plus 360. So that is a 720 degree. So again it is 0 degree. And C phase is 360 degrees, again 0 degree. So that is called the zero sequence component. Third harmonic is zero sequence component. So when we say there is a ground fault or zero sequence component, then we can say third harmonic is present during a phase to ground fault. Right? Normally we use these terms in a many in a such type of the fault conditions, and even that in lightning arrestor leakage measurement, we can say third harmonic measurement. Third harmonic measurement. Okay. Some manufacturers says third harmonic resistive component measurement, which means the capacitive third harmonic also they segregate the capacitive component and resistive component. So that is again it is a phasor. Third harmonic phasor. The third harmonic phasors, and then they calculate the real component plus imaginary component. So imaginary component will be out, only the resistive components will be get considered for the measurement, and that is the right measurement. Okay, so that is how the third harmonic 0 degree, 720 degree, 360 degree. So that is called zero sequence. So positive sequence, fundamental second harmonic negative sequence, third harmonic zero sequence, then fourth harmonic positive sequence, fifth harmonic negative sequence. And transformer over excitation conditions, the core is getting saturated. The severe heating will be get starts. Why the severe heatings will be get start when the core is getting saturated? Because the negative sequence current will be high, the losses will be very high inside. So that the core, the severe heating starts into the transformer cores. So that is how the fifth harmonic, you look at it here. So that is why we can set the fifth harmonic also into the transformer differential relay. Sixth harmonic zero sequence. Seventh harmonic, again positive sequence. So positive, negative, zero, positive, negative, zero. That is how you look at it here. Okay, so you look at it, the fundamental component, the waveform is such a way like, then 40% second harmonic is added, the waveform is got distorted. You look at it here, fundamental waveform here, and this is second harmonic, 40%. The waveform is got distorted. When there is a CT saturation, for example, say, we can find the second harmonic component will be a high during a CT saturation, second and third both. Okay. So this you look at it, the saturation is such a way that third harmonic, yes, 40% of third harmonics, 40% of fifth harmonic. You look at it here in a fundamental waveform. So you look at it here, the second, third, and fourth, which harmonic distort the waveform more. So when you can go to see the higher order waveforms, like fifth harmonic, sixth harmonic, seventh harmonic, ninth harmonic, something, जो हायर हार्मोनिक्स का ऑर्डर है वो वेवफॉर्म को ज्यादा डिस्टॉर्ट करता है. फॉर एग्जांपल से सेकंड हार्मोनिक 40% एंड 10th harmonic for example say 5%, the distortion will be high even though that only the 5% of 10th harmonic, but the distortion will be get more in that case, total harmonic distortion. So second harmonic, third harmonic, fifth harmonic, you look at it here. Okay, so according to IEEE standard 100-1992, the distortion factor is equal to the sum of squares of amplitude of all harmonics. जो जितना भी harmonics है उसका sum करके उसका square करो and divide by the square of fundamental amplitude. The fundamental component है उसका square and that whole the brackets into under root. So under root of sum of the squares of amplitude of all harmonics divided by square of the fundamental amplitude into 100%. That is called the distortion factors. So distortion factors is also more important for the equipment to equipment and in a power system network. Like 220 kV network में कितना होना चाहिए, 400 में कितना होना चाहिए, HVDC अगर लगाया है तो उसमें किस तरीके से होना चाहिए. So that has to be that harmonic, the distortion factor has to be defined for the network. Otherwise, it will damage the equipment and lines and cables in that case. That will be a frequent failures of the equipments. Similarly, IEEE standards 159-1992 also gives the many recommendations of the harmonic limits of the equipments that you can, if someone is interested, they can go to 519-1992. Okay, how the harmonics introduced? So non-linear loads, just DC loads, then variable frequency drive in a power plant, even in a chemical industry. Smelter loads, normally copper plant, aluminum plant, big, it's smelters is there. So smelters, which means nothing but it's a rectifier transformers, and then DC loads on downstream sites. So that is called smelter loads. Then high reactive load, like for example, this is starting of the induction motor. So induction motor start होती है low power factor पे, 0.2 power factor है, 0.3 power factor है, 0.1 power factor है. So it draws the more reactive powers, but parallelly it distorts the waveform also. Switching of electrical networks, like switching of any electrical network like transformer charging, then so any breaker closing, then motor starting, capacitor switching, inductor switching. So that's any switching of electrical networks that introduce the harmonics. High capacitive current. Yes, shunt capacitor bank starts. That is called the high capacitive current. That distort the harmonics. नॉर्मली जहाँ पे स्मेल्टर लोड्स होता है ना वहां पे पैरेलल में कैपेसिटर बैंक लगा रहता है क्योंकि स्मेल्टर लोड्स में रिएक्टिव पावर बहुत ज्यादा ड्रॉ कर रहता है उसको कॉम्पेंसेट करने के लिए पावर फैक्टर बहुत लो चला जाता है तो उसको कॉम्पेंसेट करने के लिए कैपेसिटर्स लगाने पड़ते हैं तो वो पावर डिस्टॉर्शन भी हाईली होता है इसमें हार्मोनिक्स इंट्रोड्यूस ड्यूरिंग रिएक्टर स्विचिंग हार्मोनिक इंट्रोड्यूस ड्यूरिंग अ स्विचिंग ऑफ HVDC लिंक harmonic introduced during power system faults and harmonic introduced during unbalanced phasor loading. अनबैलेंस में क्या हो रहा है अनबैलेंस में भी जब आपका अनबैलेंस हो रहा है तो यू सी द सीक्वेंस कंपोनेंट जैसे जैसे आपका अनबैलेंस बढ़ेगा वैसे वैसे आपका नेगेटिव सीक्वेंस करंट बढ़ता है फॉर एग्जांपल से व्हाट इट डज मीन दैट इट इंट्रोड्यूस द अदर हार्मोनिक्स इनसाइड द फंडामेंटल क्वांटिटी इज लेस आपका आरएमएस वैल्यू कम उतना ही का ये आरएमएस वैल्यू आपका बढ़ता जाता है ओके टोटल ओके हार्मोनिक इंट्रोड्यूस्ड इन इलेक्ट्रिकल नेटवर्क्स so total harmonic distortion allowed in 400 kV network is less than 1.5% and in 220 kV network is less than 3% in India. Power quality meter should measures up to 50th harmonics in 400 kV network and measures up to 25th harmonic in 220 kV network. उतना हार्मोनिक्स अगर पावर क्वालिटी मीटर अगर लगाया है तो उतना हार्मोनिक्स का मेजरमेंट्स का कैपेबिलिटी होना चाहिए 400 kV में 50 तक जाए और 220 में 25th हार्मोनिक तक जाए effect of harmonics in rotating machines so harmonics voltage is increased heating say due to the iron and copper losses in the machine at higher frequency yes it increased the heatings due to the iron and copper losses high iron and copper losses harmonic current in a motor can give rise to high air audible noise actually sometimes we see the humming sound if harmonics are significant the noise we can see the humming sound or higher audible noise the harmonic current also produced a resultant flux distribution in the air gap which can cause or enhance the phenomena called cogging which means it is refusal to start the smoothly वो smoothly start नहीं होगा उसका kick एकदम high चला जाएगा because the residual flux is still there और अब जब हम इंडक्शन मोटर्स को हम स्टार्ट करेंगे और ट्रांसफार्मर को भी अगर स्टार्ट किया तो वो इनरश करंट इज वेरी हाई तो नॉर्मली इन इंडक्शन मोटर्स में द कंडीशन कॉल्ड कोगिंग कंडीशन और क्राउलिंग व्हिच मींस वेरी हाई स्लीप व्हिच मींस it is work as good as like induction generator condition something like that okay very high sleep conditions it draws huge reactive power in that case the harmonic current pairs such as the 5th and 7th have the potential of creating mechanical oscillation in a turbine generator combination or in a motor load system 5th and 7th harmonic अगर जनरेट कर रहा है तो that will be a severe oscillation mechanical oscillation in turbine generator it is a torsional torque जो हम बोलते हैं that is how the torsion is there the effect of harmonics in a transformer machine if we apply the harmonics to the transformer it may result in increased levels of audible noise. Similarly, in a induction rotating machine, यहाँ पे भी वो humming sound transformer में ज़्यादा बढ़ेगा इसमें. The harmonic current causes the copper losses and stray flux losses, and voltage harmonic causes an increase in iron losses. Voltage harmonic से iron losses बढ़ेगा and current harmonic से copper losses and stray losses ज़्यादा बढ़ेगा. Ultimately, it is a severe ratings into the transformers. According to the C57.12, 1987 and 1989, it proposed a limit on harmonics in transformer current with the upper limit of the current distribution factor set 5% of rated current. मतलब 5% विस्टैंड उसका ट्रांसफार्मर का विस्टैंड जो है वो उतना तक का होना चाहिए कि उसको कुछ ना हो. इतना अगर टोटल हार्मोनिक डिस्टॉर्शन होता है तो. But that is on the load condition. In no load condition, it has to be a 10%. Again, the standard also gives the maximum RMS over voltages that transformer should be able to withstand in steady state 5% at rated load and 10% at no load. So, एक हो गई आपके ट्रांसफार्मर नॉर्मल रनिंग कंडीशन, सेकंड हो गया ट्रांसफार्मर ऑन नो लोड कंडीशन. नो लोड कंडीशन में डेफिनेटली हार्मोनिक्स ज्यादा ही होते हैं क्योंकि वो इनरश करंट है. इट हैज टू बी अ विथस्टैंड, ट्रांसफार्मर हैज टू बी अ विथस्टैंड. मैंने कई बार देखा हुआ है कई ट्रांसफार्मर चार्ज, स्पेसिफिकली जनरेटर ट्रांसफार्मर, वो चार्ज करने के टाइम ही वो फेल हो गया है ट्रांसफार्मर, राइट. Okay, power system faults. So, what is a fault? Fault is any failure that interferes with the normal flow of current to the load. That is called fault. So, current in most fault, a current forms between two or more phases. Normally, if it is multiple phases, it is phase-to-phase fault. If it is if it is with ground, then it is, or neutral, if it is phase to ground or phase to neutral. New path is usually a low impedance, therefore excess amount of current may flow. Obviously, जो जहां पे शॉर्ट हुआ है उसका इंपेडेंस कम है, वो ब्रांच का, तो वो ब्रांच का जो इंपेडेंस कम है तो उससे करंट ज्यादा फ्लो होने लगता है. सो I equal to V by Z, Z of the shorted path is very less. So when we see the small network, that is generator, then cable, breakers, then distribution transformers or transformers, and then there is a load. So I load is equal to V divided by Z load. So suppose V Ln is equal to 63 volt and Z load is equal to 63 ohms, then I load is equal to 1 ampere. What it does mean that the rated VA per phase is equal to 100 VA. What it does mean that the 60 जो VLN is equal to 63 ohms, we have 63 watt, Z load is equal to 63 ohms, and I load is equal to 1 ampere. So this is within 100 VA. That is called the normal load condition, because normal load में जितना सोर्स का VA है उससे कम VA पावर में जा रहा है. जैसे 100 VA का सोर्स का कैपेसिटी है and load is 63 VA, 70 VA, something like that. So impedance of source is equal to impedance of load maximum. That is called the load condition. When there is a fault, IF, you look at it here in the same network. then the impedance is got now reduced from 63 ohms to 2 ohms. So IF is equal to VF divided by ZF. So VF is equal to 40 volt, ZF is equal to 2 ohms. So IF is equal to 20 amperes. Now if you look at it, the VA comes around the 800 VA. 800 VA is higher than the 100 VA because source capacity is 100 VA and required VA to feed the fault is 800 VA. That is called the fault condition because source do not have capacity to feed the 800 VA continuously. That is for the short time rating is for either for 1 second or 1.5 second or 2 seconds maximum. So that is called the abnormal condition or fault conditions. Okay, types of this faults. So one is symmetrical faults, another is asymmetrical faults. Normally the three-phase fault and three-phase overload is say symmetrical faults. You look at it here. This is three-phase fault. So three-phase fault, you look at it, is symmetrical fault. Why? Because all three phases are having an equal magnitude at part of equal phase distribution. उसका इक्वल मैग्नीट्यूड है तीनों तीन का और तीनों तीन का फेजर्स भी इक्वली अपार्ट है. So that is why it is called the symmetrical fault. When there is a symmetrical fault, then we have seen in our slides the positive sequence component will significantly will be high. Negative and zero sequence will be a absence or significantly low. That is why we say it is absence. Source requires very highest MVA power to feed this fault because it is a three-phase. So three-phase fault is got short-circuited. So now the impedance path of the all the three phases are get down. So the VA capacity is now required very high to feed this fault. So it requires highest MVA to feed this fault. And that is why the system stability will lose faster compared to the phase to phase and phase to ground fault. That is why we can say the three-phase fault it is a severe fault. The percentage of the damages will be very high. Percentage of damage will be a very high, even in a generator side as well as on the fault side, both the side, because energy is very high. Energy is high, so damage will be very high. Very rare fault in a overhead line. Overhead line में कभी हमने थ्री फेज फॉल्ट ऐसा डायरेक्ट मैंने तो देखा नहीं. थ्री फेज फॉल्ट पहले फेस टू फेस क्रिएट होता है या तो फेस टू ग्राउंड क्रिएट होगा. कोई एक पोल है, पोल के ऊपर तीन फेज ऊपर नीचे कनेक्टेड है, तो कोई एक पोल के ऊपर से कोई एक कंडक्टर स्नैप गिरेगा, वो दूसरे कंडक्टर के ऊपर आएगा, तीसरे कंडक्टर के ऊपर आएगा. So it is actually evolving fault. First it is a phase to ground fault or phase to phase fault and then converted into the three phase fault. But directly three phase fault तो कहीं होता नहीं. That is except human error. अगर कोई जगह पे शॉर्ट सर्किट टेस्ट किया और उसने तीनों तीन फेज में शॉर्ट का कॉपर लिंक लगा दिया है and then एक्साइटर ऑन किया तो वो थ्री फेज फॉल्ट है. But that is a human error. Those kind of things. थ्री फेज फॉल्ट डायरेक्ट थ्री फेज फॉल्ट होने से पहले या तो फेस टू फेस फॉल्ट होता है या फेस टू ग्राउंड फॉल्ट होता है ओवरहेड लाइंस. Yes, similarly if you look at it into the cable also, थ्री फेज फॉल्ट जो एमवी स्विच गियर क्यूबिकल है उसमें भी नॉर्मली क्या हो रहा है कि मान लो कि कंडक्टिविटी ज्यादा है, मॉइस्चर है आ गया है क्यूबिकल के अंदर, तो फेस टू ग्राउंड फॉल्ट होता है या फेस टू फेस फॉल्ट होता है. उसका आर्क का लेंथ है, आर्किंग फॉल्ट है नॉर्मली. सो आर्क का लेंथ अगर बहुत ज्यादा रहता है तो वो तीसरे फेस को भी अफेक्टेड कर देता है इन दैट केस. तो मैंने कई वेवफॉर्म्स देखे हुए हैं कि जिसमें फर्स्ट साइकिल्स में थ्री फेज फॉल्ट नहीं हुआ है, बट सेकंड फेज फॉल्ट होता है या फेज टू ग्राउंड फॉल्ट होता है, द सेकंड थर्ड साइकिल से वो फेस टू फेस थ्री फेज फॉल्ट पिक्चर्स में आ जाता है एक्चुअली. So it is called as evolving fault, and evolving fault is most important to analyze and to understand the relay behavior, because relay behavior इसमें मैक्सिमम चांसेस है कि वो माल ऑपरेट करता है इवॉल्विंग फॉल्ट में. उसको समझ में नहीं आता है कि फेस टू फेस फॉल्ट है, फेस टू ग्राउंड है, अभी मुझे क्या करना है, तो माल ऑपरेट होता है. उसका टाइमिंग्स में वेरिएशंस आता है, उसका पिकअप्स में वेरिएशंस आता है. सो दैट इज हाउ चांसेस उसमें रहते, एरर्स के चांसेस उसमें बढ़ जाते हैं. Prime mover will be get damaged more if the fault persists for longer period in case of the three phase fault. All over it is high impact, commercial impact, because it is effect on the prime mover plus generator both, equipment both. Fault required to isolate as quickly as possible. अगर 400 kV नेटवर्क है तो ये फॉल्ट 100 मिली सेकेंड्स के अंदर क्लियर हो जाना चाहिए. 220 kV नेटवर्क है तो 165 मिली सेकेंड्स 170 मिली सेकेंड्स में क्लियर हो जाना चाहिए. नॉर्मली जो स्विच गियर्स एंड क्यूबिकल्स होते हैं उसमें इसका इफेक्ट बहुत हाई रहता है. द रीजन इज दैट कि उसका आर्किंग बहुत ज्यादा रहता है अंदर मेटल में. एक तो मेटल क्लेड इक्विपमेंट स्विच गियर है, उसमें टेम्परेचर एकदम से फटाक सा बढ़ जाता है और मेटल को मेल्ट कर वेल्ड एंड मेल्ट जैसा कंडीशन हो जाता है. So in that case, it has to be isolated very quickly as possible, as in 70-80 milliseconds. Okay, so if you look at it, a three-phase fault. So this is in the left side. You see the three-phase fault. So I equal to E by Z in that case, without fault resistance. Three-phase fault without fault resistance. And right side, you look at it here. Fault resistance is got introduced, RF. So I equal to E divided by Z plus RF. So normally if we consider the fault amount, that is with the, normally we do the short circuit study in a software, we consider a extreme conditions like 30 kiloampere, like bus bar की capacity अगर मुझे decide करनी है तो I can go for the worst case scenario is 30 kiloampere, 40 kiloampere for example sir, right? But जब मैं relay calculation कर रहा हूँ, relay settings कर रहा हूँ, in that time I need to also see the fault resistance, whether the fault resistance has to be comes into the pictures in which way, and what should be the maximum or minimum fault current in that case, because relay has to work on maximum fault current as well as minimum fault current. Specifically when we talk about the inverse time over current relay, which works on timings are vary with according to the current magnitude, then it is more significant. So I equal to E by Z plus RF. Okay, now if you look at it here, the right side, it is load condition, the vector, where VA, VB, VC. So VA is 63 volt, VB is 63, VC is 63, IA is 1 ampere, IB is 1 ampere, IC is 1 ampere, and 10-20 degrees lagging. You look at it here. So normally this is called the normal load condition or normal operation. When there is a fault, then you look at it here. VA is reduced from 63 to 30 volt. VA, VB, VC is got reduced. IA, IB and IC is got higher. ये बढ़ गया एकदम, IAIB IC बढ़ गया है। एक्चुअली हम रिले में कई बार लॉजिक भी लेते हैं कि थ्री फेज फॉल्ट डिटेक्शन जो करनी है उसमें फेस टू फेज एंड फेज टू ग्राउंड के लिए तो डिटेक्शन के लिए सिमेट्रिकल कंपोनेंट कम यूज कर पाते हैं। थ्री फेज के लिए क्या करेंगे? सो थ्री फेज के लिए हम लोग नॉर्मली रिले में लॉजिक्स लेते हैं कि पॉजिटिव सीक्वेंस करंट विल बी almost more than 80%. Negative and zero sequence is less than 20%, and phase current is higher than the 1.2 times or 1.5 times, and the voltage is less than this, then it considered as a fault condition, not a load condition. So that is called a three-phase fault condition identification. Three-phase loop has to be calculated. So that is how the three-phase loop will be calculated in that case. So look at it here. There is typically two bus system, two generator, two source system, two source, two bus, G and H, and there is a line between the G and H bus. So when there is a fault F, so at fault location, the voltage is almost zero. Look at it here. Voltage is almost zero. The positive sequence voltage is almost zero. When you go far or away from this fault location, the positive sequence component is getting increased. V1 voltage at both the end. दोनों साइड पे V1 इंक्रीज हो रहा है। इसका मतलब मान लो रिले आपका G बस बार है उससे पहले लगा है, वो इतना पॉजिटिव सीक्वेंस वोल्टेज देखेगी। जो H से पहले लगा हुआ है वो भी पॉजिटिव सीक्वेंस वोल्टेज देखेगी। बट अगर फॉल्ट लोकेशन के ऊपर अगर आप देखोगे तो वोल्टेज इज ऑलमोस्ट जीरो है। ऐसा आप मान लो कि ट्रांसफार्मर से पहले आप आ जाते हो या ऑलमोस्ट ट्रांसफार्मर के नजदीक वाई साइड आप आ जाते हो, then you see the voltage almost you get a 60% voltage. So this is how you look at it here. The V1 profile is getting changed. When you go away from the fault, the V1 is getting increased. Okay, this is how simulation I can show in a one network of, there is a one power plant. It is 660 megawatt machine, and there is a unit transformer. And then in a unit transformer, you look at it here, the unit auxiliaries. And then the fault is created on motor terminal of BFP motor. And you look at it here, the relay operation. The BFP motor relay operates in 50 milliseconds. The upstream relay operates in a 0.26 millisecond. And then the HV side of the UAT operates in a 0.55 milliseconds. And you see here, the fault current is 23 kiloampere, 23.993 kiloampere. The fault current. The city ratio is 700 by 1. So fault current is 23.993 kiloampere in all three phases. And the fault voltage is 241 volt. Now you look at it here, when the fault voltage is 241, fault current is 23.993, you see the phasor diagram. You see the phasor diagram, and you look at it here, the impedance is 0.01, 0.01, 0.01 in all three phases. ZA, ZB, ZC, ZAB, BC, CA. Now, if you look at it, the system symmetrical component, it is positive sequence component is 23.993 kiloampere at the rate minus 84.6 degree. Negative and zero sequence current is almost zero. Similarly, the positive sequence voltage is 241 volt at the rate minus 0.3 degree, and negative and zero sequence voltage is 0. So you look at it here, the positive sequence component is significantly high. The negative and zero sequence component is very low, almost 0. So look at it here, the sequence component is 241, 241, 241 VABVC voltage. Now you see the V1 voltage. V1 voltage is positive sequence voltage is 241, V2 is 0.07, V0 is 0.07. So red color, you look at it here, red color bar is V1, and the another red color bar is for I1. So I1 is significantly high, I2 and I0 is 0. Similarly, V1 is very high, V2 and V0 is 0. Okay, what is asymmetrical current? Asymmetrical current, which means तीनों तीन फेस का मैग्नीट्यूड इक्वल नहीं है और तीनों तीन फेस का फेस एंगल्स भी इक्वली अपार्ट नहीं है. So that is called the asymmetrical faults. This is happening due to the DC component and unbalanced fault conditions. High DC component. जब डीसी कंपोनेंट जनरेट होता है ना, तो वेवफॉर्म को एक साइड लिफ्ट होना शुरू हो जाता है. When it is lifted on one side, then it is basically sinusoidal properties, वो फंडामेंटल जो बैलेंस कंडीशन है वो निकल जाता है, एंड इट विल बिकम एक साइड का, मान लो कि पॉजिटिव साइड में अगर खींचा है वेवफॉर्म, तो पॉजिटिव साइड में वो 10 एम्पियर दिखेगा, द नेगेटिव साइड में वो इट विल बी अ वेरी लेस 3 एम्पियर्स दिखेगा. सो व्हेन वी सी द फेजर्स, then it shows the 10 ampere, but that is the phase angle will be a different. So due to the high DC component, the phase angle is shifting, and due to the magnitude, unequal magnitude, the magnitudes are also all three phases will be a different. अनबैलेंस फॉल्ट मतलब फेस टू फेस फॉल्ट हुआ है, तो दो फेज में ज्यादा करंट दिखेगा, एक फेज में कम दिखेगा. फेस टू ग्राउंड फॉल्ट हुआ है, एक फेज में ज्यादा दिखेगा, बाकी के दो फेज में कम दिखेगा. तो उसमें आपको अनइक्वल मैग्नीट्यूड एंड अनइक्वल फेस एंगल डिफरेंस मिलेगा. सो दैट इज हाउ वी से इट इज asymmetrical fault. Normally, positive and negative sequence component will be significantly high in phase-to-phase fault, and positive, negative, and zero sequence component will be significantly high in a phase-to-ground fault. Phase-to-phase fault में zero sequence component वहाँ पे नहीं मिलेगा. Fault resistance will be present and higher in case of phase-to-ground fault. फेस टू ग्राउंड नॉर्मली ट्रांसमिशन लाइन में जितने भी फॉल्ट्स होते हैं वो 70-75% फेस टू ग्राउंड फॉल्ट है. इवन केबल्स में जो फॉल्ट होता है उसमें से काफी मेजॉरिटी फॉल्ट्स आपको फेस टू ग्राउंड ही मिलता है. इवन दो वी सी इन एवरी स्विच गियर दो फेज अफेक्टेड है या तीन फेज अफेक्टेड है, बट मैक्सिमम इट स्टार्ट्स फ्रॉम द फेस टू ग्राउंड. मैक्सिमम द फॉल्ट स्टार्ट्स फ्रॉम फेस टू ग्राउंड एंड कन्वर्टेड इनटू फेस टू फेज और थ्री फेज फॉल्ट. So phase to ground fault will be with overhead line 70 to 75% say. The fault resistance will be higher in a transmission line, and fault resistance will be very less in case of the underground cable. Underground cables में fault resistance बहुत ही कम मिलता है, इसके लिए वो bolted fault है. जब भी अंडरग्राउंड केबल और स्विच गियर्स में जो एमवी स्विच गियर्स या एलवी स्विच गियर्स में जो फॉल्ट होता है वो बोल्टेड टाइप का फॉल्ट होता है, उसमें मेल्ड एंड वेल्ड का कंडीशंस ज्यादा रहता है. So if you look at it here, again, the face-to-face, face-to-ground fault convert into face-to-face fault or three-phase fault due to the damages of mechanical structure and dislocation of conductors. वो ज्यादातर देखने को मिल रहा है ट्रांसमिशन लाइंस में, इवन इन स्विच गियर क्यूबिकल्स में भी. If you look at it here, this is, if there is a face-to-face fault, this is VA, VB and VC. You look at it here. IC and IB fault है. So VB and VC कम हो गया है. IB and IC higher है, and it is opposite side of IC is opposite side of IB, or IB is opposite side of IC. So IC is equal to minus IB in that case. IA is equal to almost considered as a zero in a two-bus network. Similarly, you look at it here. So when there is a fault location F, the positive sequence component is almost divided by 2. When you go far away from this, the positive sequence voltage is getting increased, the negative sequence voltage is getting decreased. फॉल्ट लोकेशन के ऊपर अगर आप देखोगे तो पॉजिटिव सीक्वेंस वोल्टेज डिवाइड बाय 2, नेगेटिव सीक्वेंस वोल्टेज डिवाइड बाय 2. बट जब आप उससे दूर जाने लगते हो, मतलब रिले का लोकेशन अगर उससे दूर है और उससे भी दूर है, आगे का रिले है, तो वो अलग अलग वे में वोल्टेज देखेगा. उसको V1 ज्यादा मिलेगा, V2 कम मिलेगा इन दैट केस. Okay, so you look at it here, there is a face-to-face fault. There is a face-to-face fault, and then there is IF1 is equal to minus IF2. So look at it into this network. जो हमने थ्री फेस में जो सिमुलेशन किया था, सेम सिमुलेशन फेस टू फेस में भी किया है, फेस टू फेस फॉल्ट रन करके किया है. तो उसमें इफ यू लुक एट इट हियर, द IA करंट is 20.996, IB current 20.546, and IC current is 553. IA voltage is 2.86 kV, IB is 2.88 kV, and IC is 5.72 kV. इसमें जो आपने फेस टू फेस में वहां पे 23 किलो एम्पियर्स देखा, 23.9 किलो एम्पियर्स तीन फेज में, उसमें यहाँ पे फेस टू फेस पे 20.996, 20.554 किलो एम्पियर A and B में है, C में is 553 amperes. So this is how you look at it. The phasors is exactly opposite current IA and IB. You look at it here. And impedances, you look at it, ZA is 0.14, ZB 0.14, ZC is 10.55, is very high, and ZAB is very low, 0.01, ZBC is 0.43, and ZCA is 0.4. Now you look at it here, is face-to-face fault. The positive sequence component is 12.1 kiloampere. The negative sequence component is 11.83 kiloampere. Fault current is 20.9, but positive sequence is 12.1 kiloampere. Negative sequence current is 11.3. Almost both are the same. Similarly, the positive sequence voltage is 2.9 kV. The negative sequence voltage is 2.7 kV, and zero sequence voltage is 0. So this is how you look at it here in a voltage when current bars. The phasor value of voltage is 2.8 kV A phase, 2.88 kV B phase, 5.72 kV C phase. Current is 20.99 is A phase, 20.54 kiloampere is B phase, and 543 ampere is C phase. Whereas symmetrical component, if you look at it, A phase is 2.93 is red color bar, and negative sequence component is 2.73 is yellow color bar. You look at it, V1, V2, and V0 is almost very less. You see that it's, we can ignore this thing, that V0. Similarly, I0, I1 is 12.15 kiloampere, I2 is 11.8 kiloampere, and I0 is very less, it is just 4 ampere. So red color bar of right side and yellow color bar of right side, you look at it here. This is I1 phase fault. Okay. लंबा साहब, हेलो
यस सर।
सर, ब्रेक ले करना है कि कैसे करना है सर?
हाँ हाँ सर, ये 90 मिनट्स का हमारा पहला सेशन था।
हाँ,
वो तो हो चुका है होगा।
हाँ,
आप इसमें आप क्वेश्चन आंसर्स ले लीजिए थोड़े से, यदि किसी के हैं तो उसके बाद ब्रेक कर दीजिए करीब 15 मिनट, 10-15 मिनट में।
ठीक ठीक ठीक
और ब्रेक करके सेकंड जो हम शुरू करेंगे 2:30 बजे करेंगे सर।
ठीक है सर, नो
2:30 से फिर वो 90 मिनट्स का वही होगा, और उसके बाद एक क्वेश्चन आंसर्स वगैरह हैं।
ठीक है सर, ठीक।
यस।
हेलो
पार्टिसिपेंट्स, आवाज आ रही है आपको?
यस सर।
आ रही है सर।
यस
सर, any question till?
ये फॉल्ट लोकेशन से वोल्टेज किस डायरेक्शन में हायर होगा, किस डायरेक्शन में लो रहेगा?
सर, अभी तक का जो प्रेजेंटेशन हुआ है और डिस्कशन, उसमें सर कोई क्वेश्चन है आप लोगों को?
हाँ जी सर। सर, ये फॉल्ट लोकेशन से वोल्टेज किस डायरेक्शन में हायर होगा, किस डायरेक्शन में लो रहेगा सर?
नहीं, फॉल्ट लोकेशन से सर बताओ आप फिर से।
सर ये आपने बताया ना कि दो हमारे ट्रांसमिशन लाइन के पॉइंट्स हैं।
हाँ,
ट्रांसफार्मर के बीच में एक पोजीशन पे फॉल्ट अकर होगा, अर्थ फॉल्ट।
हाँ,
तो किस डायरेक्शन में हमारा वोल्टेज हाई होगा सर?
हाँ, इसमें सर देखो, जहाँ पे ये देखो, अभी आपको स्लाइड दिखाई दे रहा है ना, यू सी दैट। उसमें अगर आप देखो तो फॉल्ट लोकेशन के ऊपर अगर आप देखोगे पर्टिकुलरली वहां पे, राइट, तो वहां पे आपको जैसे फेस टू फेस फॉल्ट है तो उसमें पॉजिटिव सीक्वेंस वोल्टेज डिवाइड बाय 2 एंड नेगेटिव सीक्वेंस वोल्टेज डिवाइड बाय 2, मतलब आपको वो जगह पे पॉजिटिव एंड नेगेटिव सीक्वेंस का इक्वल वोल्टेज मिलेगा। ओके, जैसे आप फॉल्ट लोकेशन से दूर जाते, मान लो कि आपका ये लाइन है, अभी ट्रांसमिशन जी एंड एच के बीच में ट्रांसमिशन लाइन है 100 किलोमीटर का, उसमें आपको 50 किलोमीटर मिड पॉइंट के ऊपर एक फॉल्ट हुआ है। तो when you see the fault at midpoint, okay, then the value will be equal. जैसे ही आप वो फॉल्ट लोकेशन से यहां से आप 80 किलोमीटर दूर जाते हो और वहां से आप 70 किलोमीटर दूर जाते हो, तो फिर दोनों में V1 बढ़ता जाता है, V2 डाउन होता जाता है।
ओके सर।
आप रिले के ऊपर देखोगे तो उसके हिसाब से मेजरमेंट है।
राइट।
क्योंकि रिले तो आपका मान लो कि 50 किलोमीटर दूर लगा है एक रिले, दूसरा रिले 50 किलोमीटर दूर यहाँ से लगा हुआ है, समझो, राइट। और उसके आगे का रिले, एडजेसेंट लाइन का आगे का रिले है जो इसको जोन 2 देख रहा है, वो उससे 30 किलोमीटर या और 50 किलोमीटर दूर लगा हुआ है। तो टोटल पहला रिले लगा है वो 50 किलोमीटर है, जो सेकंड रिले लगा है वो 100 किलोमीटर है। जो पहला 50 किलोमीटर वाला रिले लगा है वो V1 मान लो कि उसने 30% पढ़ा, जो 100 किलोमीटर वाला लगा है उसने 50%, 55% V1 पढ़ा।
ठीक है।
एनी मोर क्वेश्चन प्लीज? यदि अभी क्वेश्चन नहीं है तो यू कैन नोट डाउन, एंड सेकंड सेशन में भी आप क्वेश्चन आस्क कर सकते हैं, पूछ सकते हैं। अभी क्वेश्चन को नोट कर लीजिए आप लोग।
ओके सर, ओके।
वो भी कर सकते हैं, यदि अभी इमीडिएटली पूछना तो अभी भी पूछ सकते हैं। बोथ ऑप्शन आर यू। यदि कोई क्वेश्चन नहीं है तो वी कैन क्लोज इट फॉर फर्स्ट सेशन।
ओके।
दवे साहब, मुझे लगता है कि जब क्वेश्चन किसी का नहीं है तो नाउ वी कैन क्लोज इट एंड वी विल स्टार्ट एट 2:30.
No problem, sir. Right?
Yes. Then we will start again at 2:30 sharp and kindly be with us at 2:25. Thank you.
Okay. Okay.